This video is a continuation from last week's videos on modeling for EK210. Last week we got an introduction to some of the preliminary concepts of modeling, and we talked about many different kinds of models that you could use in your engineering design. This video is about modeling for the IR thermometer, and the following video will be about modeling for the pulse oximeter. In your next assignment, you'll be asked to model two aspects of your design as part of the preliminary design phase. We're done with the conceptual design, which means you've selected your means, and now it's time to figure out if your conceptual design will work and how you'll produce reasonable specifications for the product components. The example in last week's video describing design of a slingshot included several different math models that were useful in preliminary design. Unless usefulness of those models is a term that means that the output of the model helps to inform your design choices. So what did we model for the slingshot? First, we modeled the mechanics, solving two-dimensional equations of motion, particle motion under fixed acceleration to determine the necessary velocity of the projectile. Once we had that, we could model energy, constructing a balance between the required projectile kinetic energy and the elastic band potential energy needed to propel the projectile at the right speed. And then we modeled strength of materials. We employed a finite element model to determine the peak stress and peak deflection in a CAD representation of our design, and we managed to find out that our original assumption that polymer might be a good choice was wrong, and we chose instead an aluminum design for our slingshot. So in this video, we'll go through detailed models that can be used to aid in the design of the IR temperature sensor. Our intention is that you could use these models when you try to think about, as a template, when you try to think about how to model your pulse oximetry project. You're not bound by these examples, but you will need to model two aspects of your design for the assignment. What can we model for the IR thermometer? I think a really good choice is to model the radiant heat transfer from the forehead to the sensor. We'll start by stating what we know. Hot objects radiate heat, and the sensor measures that heat. We know that heat flux is proportional to the difference between the fourth power of temperature of the source and the fourth power of temperature of the sensor. Maybe you didn't know that, but you know it now. What will be the effect of standoff distance on measured temperature, and how can we model it? Well, the first thing to do is to decide what do we know and what can we assume. Well, let's assume something about the forehead itself. Let's say the forehead is about 100 millimeters square. Most foreheads aren't square, but we'll just use that to simplify things. And let's assume that the forehead is at a constant temperature. Let's say that the forehead temperature is 37.5 degrees, which we determined was the threshold for fever, and that it's constant and uniform across the forehead. Let's assume that the sensor field of view is 90 degrees. We'll justify that assumption in a minute. And then let's assume that the background, everything other than the forehead, is at 20 degrees C, including the sensor itself. And now you say, well, I haven't taken a course in heat transfer yet, so you're going to give me some big equation in heat transfer. It's not what we're going to do. What we're going to do is start from what you do know. You know that the equations of heat transfer are challenging, but we can still make progress. From the datasheet, we know that the sensor somehow measures radiant heat transfer and calculates remote temperature from that measurement of radiant heat transfer. More radiant heat transfer means a higher temperature. What do you think the sensor module assumes about the remote temperature that it's measuring? The first insight we can get is that the sensor has to assume that the temperature is uniform over the whole remote field of view, because it's only giving us one temperature. So the assumption is that this sensor measures an aggregate of some of what the ununiform temperature is, but assumes that the temperature is uniform over the whole remote field of view. Okay, so it's a uniform temperature. What else do we know? Well, we know that radiant heat transfer between two bodies depends on the difference between the fourth power of their respective temperatures. So T of the source to the fourth power minus T of the sensor to the fourth power. And it also depends on their separation and their respective areas and their emissivity. It's a fairly complicated equation. But what will be the heat transfer between two bodies that are at exactly the same temperature? Suppose the source and the sensor are at the same temperature. Well, there's zero heat transfer. So for radiant heat transfer, it's important to know that if there's no temperature difference, there's no heat transfer. So if we take the forehead away or move the forehead so far away that it's a negligible part of the area that the sensor sees, and all the other items in the field of view, walls and tables, etc., are at the same temperature as the sensor should detect no heat transfer. What will it measure as the temperature if it detects no heat transfer? Well, it'll measure its own local temperature, the measured internal temperature as the remote temperature. In other words, the sensor, when it detects no radiant heat flux, just looks at its own temperature sensor and says, I'm getting nothing from the outside, therefore what I'm looking at must be the same temperature as me. So we've got two insights now. Let's get a third. What's the field of view of the sensor? Well, we can look at the data sheet and find out that the sensor has a field of view of about 90 degrees. That means that if we move a distance d away from the sensor, we have a field of view that is 2d, just from geometry. And that means that the area that we sense is 2d squared, which is 4 times d squared. The field of view we're going to denote as AS for the area sensed. Now, the area sensed is probably circular, not square, but this is a triviality and probably not important to a model of this level of fidelity. And this will make the math much easier. So, what's the temperature that we measure if the forehead fills the field of view? We move the person close enough to the sensor so that the distance d is small enough so that the whole field of view is filled by the forehead. The sensor's at an ambient temperature of T0, the background is at an ambient temperature of T0, and the insight we have is that if you have a uniform field of TF that fills the area of the sensor, then we get an accurate measurement, that T is equal to TF. The measured sensor temperature is the forehead temperature. What happens if there's nothing in the field of view? The person moves away or moves out of the field of view or moves so far away that their area of their forehead is negligible compared to the area that we're sensing. In either case, the sensor is looking at T0 now, and so clearly insight number 4 is when there's no forehead in the field of view, the sensor senses that senses the temperature of the ambient background. Sensor will get no heat transfer and will indicate the background temperature. T is equal to T0. So we've got 4 insights now. Let's move into making a model. All of these have been just trying to understand the physics, and now we're going to create a model. So what happens when the forehead doesn't fill the field of view? This is the general case we're trying to figure out. Suppose this person is standing far enough away so that they're filling up part of the field of view of the sensor, but not the whole field of view. In other words, the area of the forehead is less than the area of the sensor regard. Well, when the forehead is far away from the sensor, it radiates heat from an area that's smaller than the full sensed area. The rest of the sensed area is background, but the background does not radiate heat. So the sensor must measure some temperature that's in between the background temperature and the forehead temperature. This probably should be called Insight 5, but it's actually just an observation that if the forehead is very close to the sensor, we measure TF. If the forehead is gone from the sensor, we measure T0. So if the forehead is somewhere in the field but not filling the area, the temperature must be somewhere in between T0 and TF. That just makes common sense. So let's make up a model using our insights. Here's what we know so far. The forehead area is fixed and constant. The sensed area depends on how far away our measurement is from the sensor. If the area of the forehead divided by the area of the sensor is 0, what does that mean? The forehead is very, very far away from the sensor. Then the sensor is measuring mostly background, and so the T is T0. On the other hand, if the forehead fills the sensor, meaning AF over AS is equal to 1, then the temperature we measure is the temperature of the forehead. So, what is it that we're trying to find? What we want to know is the temperature, measured temperature, as a function of d, the distance that the forehead is away from the sensor. Notice that these boundary conditions that we learned about in the 4 bullets above don't talk about d so much as they talk about the ratio of AF to AS. But that's not a problem because AF divided by AS is a simple function of d. And we could write that equation out. What is the relationship between AF and A over AS and d? It's a simple equation. So it would be satisfactory for us to find the measured temperature as a function of AF over AS. Why do we want to do that? Because our intuition tells us that if the forehead fills the sensor field of view, we get TF, and if it's far away, we get T0, and there might be some relationship between the ratio of the forehead temperature to the sensed area that relates to temperature. So we're going to assume linearity. This is justified by the heat equation. If we'd gone through the formal analysis, we would have found that this is actually true. But it's always a good guess. Always a good guess to assume if you have two end conditions, let's assume linearity between those two end conditions. So let's fit a line to the two known data points for t as a function of AF over AS. In other words, t will be y, and AF over AS will be x, and we're going to do a y equals mx plus b linear fit. So t is equal to m times the ratio of AF over AS plus b, and solve for m and b. Well, if we put in the first known, that the ratio of AF to AS is 0, then t would be equal to b, and t is equal to T0, so T0 is equal to b. Similarly, we can find that m is equal to TF minus T0. So now we have an equation which reduces to t is equal to a function of TF and T0, and these terms for the ratio of AF to AS. Now, all of this is true and valid. There is an unusual case which happens. What if AF is larger than AS? That makes this thing a little bit unwieldy and makes for a non-physical situation. So what we have to note is that if AF is much larger than AS, meaning the forehead is much larger than the sensor area, well, the sensor will still measure a smaller portion of the forehead, and the temperature will still be TF. Okay, so that's our model. Now what do we do? Next thing we do is we'll simulate this model, this equation, in MATLAB. Let's write down this equation and then simulate it, plotting t as a function of the ratio AF to AS. It's linear like we said it would be. AF, the smallest AF is 0. The largest AF over AS is 1. And the 1 case corresponds to the forehead being very close to the sensor. The 0 means the forehead's very far from the sensor. So what do we do with this? Well, we really wanted to get t as a function of d. So we can put in the equation for AS is equal to 4d squared, and the forehead width is the square root of AF. And so the distance we could measure in millimeters, but we sometimes like to, in a model, use normalized terms. So we could say the distance divided by the forehead width, which becomes a dimensionless number, is 0.5 AS over AF square root. Well, if we plug that in, so we're just looking at the exact same data that's in this plot, but we're now going to plot, instead of AF over AS on the x-axis, we're going to plot distance from the sensor in forehead widths. And what we get is a curve that, that shows that very quickly, as we move away from the sensor, we start to drop in the measured temperature. When we're 2 foreheads away, our temperature is measuring something like 21 degrees, far less than the 37.5 that we know the forehead is at. So what is the MATLAB model? Here it is. Here's the function. These 8 or 10 lines are what we needed to plot these values. And now we have a reasonable model for the temperature as a function of distance. Okay, so how do we validate this model? We made up a model. That doesn't mean it's true. Let's figure out if it's true. First, we'll measure the temperature at a separation smaller than a forehead, half a forehead away. And at that separation, AF is equal to AS. And then we'll measure the temperature at that separation and then at larger values of separation. And we'll plot that data against our model. Does the data fit our model? And finally, we'll use the model, if it does fit, to estimate a correction factor for the sensor measurement and to set the bounds on an allowable separation. Okay, so we made up a model, we validated the model, now we use the model to try to inform our design choices. So here we go. Here's 3 things we can do to help us in design. We could compensate for the field of view temperature errors. We know now how our model predicts under-representation of temperature, and then we can fix that. Or we could design a lens in, as shown in the schematic to the left, that narrows the field of view and makes it so that we can look at a forehead very far away and still have it fill the sensor field of view. Or third, we can limit the design standoff distance, saying that in our design, the forehead has to be within 1 forehead distance of the sensor. So what other things could we model in the IRSensor? We could have modeled what are the sources of signal fluctuation and what mathematical models underpin those. We could model measurement noise. We could model motion of the sensor or the subject. We could have modeled changes in the background temperature. We could have modeled how signals vary with time under steady state conditions. We could measure the fluctuations at a high speed and try to see what they were. We could evaluate the standard deviation of those measurements and find out what was the long-term drift in the signal if the forehead stayed at the same temperature and the sensor didn't move. We could figure out how noise could be reduced and come up with models for that. We could reduce sources of signal fluctuation, such as stabilizing the sensor. Maybe we could create an artificial background. I have said that if the background is at 20 degrees, the sensor will read 20 degrees without a forehead in the field of view. It will do that better if we created an artificial background that we knew was at 20 degrees. we could average signals. So this video has been an attempt to teach you how we might model the IR thermometer with a deep dive on one model and then a whole bunch of suggestions for other models. In the next video, we'll talk about modeling for the pulse oximeter. Thank you.